All right, so we're going to go over number 40 from chapter 2 in the physics textbook. And it reads, Touchdown on the moon. A lunar lander is making its descent to moon base 1. The lander descends slowly under the retro thrust of its descent engine. It's a decent engine. I bet it's a decent engine. The engine is cut off when the lander is 5 meters above the surface, and it has a downward speed of 0.8 meters per second. With the engine off, the lander is in free fall. What is the speed of the lander just before it touches the surface? The acceleration due to gravity on the moon is 1.6 meters per second squared. So, this is an interesting concept. So, first things first, I think we need to talk about the acceleration on the moon. So the gravity is 1.6 meters per second squared. That means the acceleration is negative 1.6 meters per second squared since it's pulling it down. So A of t is equal to 1.6. Its velocity, we know its initial velocity, because we're going to say right when it hits 5 meters above the surface, that's t equals 0. That's 0 seconds. So its initial velocity is equal to negative 0.8. And that's meters per second. So we can write that there. Meters per second. And we know that it starts doing this when it's 5 meters above the surface. So that gives us initial position, which is 5 meters. So now it asks us, what's the speed of the lander just before it touches the surface? So that's going to be the speed is talking about velocity, so we need to find out when it touches the surface, and then we can plug that into a velocity function that we can calculate. So we need the velocity function, so v equals t. And then it's asking us what the acceleration due to gravity, or no, never mind, that's not a question, that's just more information. So our question, really, we need to find this, and then we need to find out, well, I think first of all, we find out when it hits the ground. So when the position is equal to 0, then that'll give us what we need to plug into here. But first we need to find this. So we have our acceleration function is 1.6, it's a constant. And so that's easy, so we take 1.6, and to find the velocity function, we simply integrate. So the integral of 1.6 dt, and that will be our velocity function, is equal to the integral of 1.6 dt. And so velocity is equal to 1.6 t. Really easy, really simple. But wait. Okay, so that's not true, because when you integrate, you have to do the plus c. You don't know when you don't know when its initial thing is, but this is velocity, and we just so happen to know the initial velocity, so we can go ahead and plug that in over here, and it'll give us 1.6 t minus 0.8. So that's our constant, and that shows us where this graph lies. Now, to find the position function, well, we don't need to find the position function quite yet. Maybe we do. We'll find it in a minute. That's well, yeah. So we do need to find it right now. But right now, I'm just going to write this up here. So v of t is equal to 1.6 t minus 0.8. So now we have a vital piece of information. Now we can find what the position function is, and we can work on that from there, because now we need to find out when it equals 0. So to find the position function, we need to take our velocity function's integral. So the integral of the velocity function, 1.6t minus 0.8 dt. And so that is going to equal, so 1.6t, integrating that, you're going to have t squared divided by 2, you're going to get 0.8 t squared minus 0.8 t plus a constant, but we know the initial position, so that is going to be a constant, which is 5 meters. So we know that position is equal to 0.8 t squared minus 0.8 t plus 5. So now we need to find out when that is going to equal 0. So I think, first of all, let's write down this function up here, and then we can have more room to work on this equation. Okay. So now, we don't really need these much anymore, but we can always look back at the book if we're wondering, or look here. So then we're trying to find when position is equal to 0, what time that is. So we can set that equal to 0. 0 is equal to 0.8 t squared minus 0.8 t plus 5. Solving for t would be very difficult. That's why we have x equals negative b plus or minus square root b squared minus 4ac all over 2a. That's going to help us solve for t. So t is equal to negative b, so negative 0.8, negative that is 0.8, plus or minus the square root of b squared, negative 0.8 squared, minus 4 times a, 0.8, c, 5, all over 2a, 0.8. So this is a bunch of mathematics, as you can tell. I mean, I hope you know, if you're watching this, that this is math. But that's going to, you work it out and you boil it down. I'm not going to go through each and every single step. Basically, well, I'll say it, I won't write it, but negative 4 times 0.8 times 5, you're going to get 16. And then this squared, it's going to give you 0.64. So 16 plus, or yeah, so this is going to be, oh, this is actually negative, I believe. Yeah. I think I goofed up, guys. I think these need to be negative. That's true, because it's moving downward. I'm glad I caught that, because that can really change your math. And so, since you have two negatives here, you end up with positive 16 and then 0.64. Then you end up with the square root of 16.64. So it's 0.8 plus or minus the square root of 16.64 all over, and that's a negative as well, negative 1.6. So t is equal to that. And so this is the point where you will split it into two different things, and you'll find out, okay, when is it going to equal 0? Because we're finding the zeros of this function. And so if you add this together, then the top number is going to be positive and the bottom number is going to be negative, and it's going to give us a negative sign for time. We're not looking for a negative sign for time. We're trying to go ahead in time, not backwards. So we're going to have to negative so that this negative and this negative cancel out and we get a positive. So what this is 0.8 minus the square root of 16.64 all over negative 1.6. That's going to give you 2.0495 seconds. So this is the time when position is 0. This is when the position of this lunar lander is going to be 0. It's when it's going to hit the ground. Okay, so that means that we can write that up here, 2.0495 seconds. So now we can plug that into our velocity and find out the velocity just before it hits the ground. So when I think just before it hits the ground, I'll think like, like the limit as the position approaches 0. Like we're trying to get as close to the ground as possible. So basically, in calculus, you figure out, you just set it equal to that. So we're going to set it equal to when it hits the ground, find out the velocity at that point. So we're going to plug this into our velocity function. So v of 2.0495 is equal to negative 1.6 times 2.0495 minus 0.8. And then you just do some math, and what it's going to give you is negative 4.0792, and that's in meters per second. And that's your answer. So this lunar lander, since it shut off its engine and it's moving still pretty fast and it gets affected by gravity, it ends up it'll be going negative 4.792 meters per second right when it hits the ground. I can't imagine that'd be a very nice landing, but thankfully this is a math problem. I don't know if this is what happened in real life with the lunar lander, otherwise that might be a little bit hectic, but I don't know. Maybe they got some pretty good suspension on that thing. But there you go, that's your answer for number 40.